So today's presentation is all about ocean currents, and this piggybacks off the lab that we just completed in class. What I need you to do is in your notebook at the top of your page, write in big bold letters the word ocean currents, and you're going to summarize the key vocabulary and the ideas and the concepts and the stories from this presentation. So let's talk about that lab, temperature lab number 3. What do we see here? And this is going to be a reinforcement for those of you that performed the lab and an introduction for those of you that weren't here necessarily. So we had this lamp here and it was given energy to water on that side of that pan. And this side of the pan was receiving no energy from the light. And what we did was we took the temperatures and we saw that the temperatures over here changed a lot because it was getting a lot of energy. Over here, we wouldn't have expected the temperatures to change too much because it wasn't getting any light. But in reality, the temperature on that side went up a little bit as well. Now, it didn't go up as much, but over here we had a temperature change of, say, something like that. And on this side, it still went up even though it didn't get any sunlight. And that's going to lead us into the discussion of ocean currents here on our planet. This represents heat transfer by convection. Over here we got a lot of energy and it makes this water here hot, and then the water moves this way and it mixes with the colder water on the other side, making it warmer, making the temperature go up even though it didn't receive any energy. And this is the same process that happens on our planet. Once again, convection. We already have this term in our definitions prior at the start of the unit, but you need to also be very aware of what convection is at this point because now it has some real world applications. This is transferring heat by convection. And in this lab, we saw that the water in the lamp got some energy and it took it to the other side. It transferred energy and it was the water that was doing it. That process is called convection. And this happens very importantly and very noticeably all over the planet. Now, what does this have to do with ocean currents? Well, ocean currents is how this process happens on the Earth itself. Now, remember what we said about Barrow, Alaska. It gets no sunlight in the wintertime, so they get very, very little sunlight, if any at all. For 67 days, there is no sun in the sky. So what should the temperature of Barrow, Alaska be like if they're getting absolutely no sunlight? It should be impossibly cold. But we know that's not true. We know that people live in Barrow, Alaska, even in the wintertime when they're not getting any sunlight. Well, how can it be warm enough? If we look at the temperatures of Barrow, temperatures are cold, sure, especially for us here in Atlanta, -2, -6, -7, but that's a livable temperature. It's not so impossibly cold that people can't survive in that. You can put on a warm enough coat and you can live in that. However, without any sunlight, we have to explain how can it get warm enough, even though you're not getting any sunlight, to have those kind of temperatures. And here's the process. I had you sketch this in the lab. If you didn't get it on the lab paper, which a lot of you did not do if you had to take it for home for homework, or if you weren't here to perform the lab, you need to make a note in your notebook about how this process happens. So we know here at the equator, you get lots of sunlight and the water there gets warm. And here's a funny thing that happens to things as they get warm, and we don't have this term in our notes yet. This idea of thermal expansion. This states that most things, not all, it's not a scientific law, but most things will expand or get bigger as the temperature rises. And that kind of makes sense because getting more energy, the particles are moving faster and they're going to spread out and they're going to try to get bigger or expand. And that's exactly what happens on the planet. The water near the equator gets warm because it's getting all the sunlight and it expands. And the way it can expand is it moves north and south away from the equator. Well, as that hot water expands, it moves away from the equator. Up here, we've got cold water. And when the hot water mixes with the cold water, they make warmer water than what you would expect up at these locations. So that makes Barrow, Alaska a little bit warmer than we would expect it to be. This goes back to that concept of thermal equilibrium. Remember that all things in nature will share energy until they have the same temperature. So that hot water comes north and it makes the cold water at the poles a little bit warmer, which makes the land around it a little bit warmer and gives you kind of livable temperatures. So this modeled Barrow, Alaska in the wintertime for us. Sunlight at the equator, convection happens, and the water expands and it moves to Barrow, Alaska, mixes with the cold water in Barrow, Alaska, and makes it a little bit warmer than we would expect. Now let's take a look at Fairbanks versus Nome, Alaska. You'll notice they are at the same latitude, so they're getting the same amount of sunlight. They're both below the Arctic Circle, so they both get some sunlight even in the wintertime. It's weak sunlight, but they still get some sun's energy. But if we notice their temperatures, Fairbanks temperatures in the middle of the state 4, 0, 13. But Nome has temperatures that are 16, 14, a lot warmer, I mean 15 degrees warmer in some cases, and that's because Nome is on the water, and that expanding hot water from the equator can move to Nome, Alaska, and bring them some energy via that process of convection. Fairbanks, too far away from the water, it can't get any energy from the equator because the water can't get near Fairbanks, Alaska. Now let's talk about Mars. Mars is a planet very similar to the Earth. It has a tilt of kind of close, I think 21 degrees compared to 23 and a half for the Earth. And Mars is close up to the sun, gets a lot of sunlight, and the equatorial regions of Mars get, just like the Earth, a lot more direct sunlight than places up here or down here. But what's different on Mars is there's no water. There's no water to move to the poles and take some extra energy, especially during times around their solstice where a pole is either most tilted towards or away from the sun. This means the poles at Mars are a lot colder than the equator because it doesn't have water to transfer energy. And you can see that in the seasons diagram. Notice in this graphic, and this is an artist rendering, it's a drawing, but it's very accurate. Notice the pole up there, when it's tilted away from the sun, it's almost completely covered in ice. And yet, in the summertime, there's almost no ice. This doesn't happen that much on the Earth. Now, sure, you get a little more snow and ice at the poles in the wintertime, but it's not like you have a mini ice age and that area is covered in snow and ice, because on the Earth, it'll stay warmer because heat from the equator can be transferred to the poles. Notice the opposite is true with the South Pole. When it is tilted away from the sun, it completely freezes over because it gets so cold because there's no water to transfer all of the sun's energy or some of the sun's energy from the equator to the poles, making it a little bit warmer. Now, this happens on Earth, and it happens with regularity, a predictable regularity. So there's a pattern to it. And that's what an ocean current is. Ocean current is a pattern of movement of hot and cold water on the Earth. Remember, the water's moving because it's hot and expanding. So an ocean current is primarily caused by the temperatures of the water and that hot water expanding. But the question is, what is that pattern? So we know that this is going to happen. Water in the equator is going to get hot. It's going to move north and south. It doesn't move east and west because all of the water in here is moving north and south. So it moves the direction it can, and that's away from the equator. But as the Earth is moving, it is spinning. And if you've ever tried to pick up and move a full bucket of water, you know the water is going to slosh out of the bucket as you try to move it. Well, the same kind of idea happens here on the Earth, that as the Earth spins, the water doesn't move in a straight line. It kind of sloshes around a little bit. The land also gets in the way. So as this water is trying to slosh around, it kind of hits the land and kind of bounces off the land. And we don't get a nice, easy, predictable, straight line expansion of water as it goes north or south from the equator. It has actually kind of a curved or a swirly path to it. That idea that the water swirls or curves as the Earth is spinning is known as the Coriolis effect. And this is about the simplest explanation for it. Is the Coriolis effect is the swirling or the curved movement of water in the oceans because the Earth is spinning, and it makes the water in our oceans follow a particular pattern because the Earth is always spinning or swirling the water in the same way. It's not like our Earth stops one day and spins the other direction or spins slower or faster. So we get something like this. The water wants to swirl in the oceans because the water is trying to go away from the equator, but the Earth spins and makes it curve. And then it hits a landmass and like, oh, I can't go through the land, so then it has to swirl back around. And this happens in all of the Earth's major oceans. You can see it here in the Pacific. You can see it in the North and the South Atlantic. You can see it in the Indian Ocean. Those swirls have a name. Those are called gyres. A gyre is a circular pattern that the water moves in the Earth's oceans. And remember, this is caused by the fact that the water is expanding at the equator, so it's moving north and south, and the fact that the Earth is spinning and it makes the water swirl around, and especially as it hits the land masses where it gets deflected. These patterns would be much different if the land masses weren't in the way, because then that wouldn't force the water to kind of be deflected. But we have land, we have water, and because of the arrangement of the water and the land on our planet, we have these nice circular patterns called gyres. They all have names, and they are creatively named for the area of the ocean in which they happen. Notice we have a Pacific gyre, but we have one in the north and we have one in the south. Same with the Atlantic. Now, the Indian Ocean doesn't have a northern component to it, so it's just the Indian Ocean gyre. One thing to notice, because of the way the Earth is shaped as it's spinning, in the northern hemisphere, these gyres spin clockwise, and in the southern hemisphere, they spin counterclockwise. Now, what does this have to do with our weather and climate? Well, if you're near a warm water current, you're going to have warmer temperatures. If you're near a cold water current, you're going to have cooler temperatures. And now we're going to talk about the most significant ocean current to us here in Georgia, and actually to the whole eastern United States. Let's set this up. We know this big bucket of water down here called the Gulf of Mexico. And it's pretty far south. It's down there by Florida. And that water gets a lot of direct sunlight because it's so far south. Well, what happens to water when it gets a lot of direct sunlight? It gets hotter. And we know hotter water wants to expand, but the water can't expand north like it wants to. And it can't expand this way either, because Mexico's in the way. So we got this big bucket of hot water there, and it's really just trying to get bigger and bigger. It's trying to push its way out of that area. So which way does it go? The only way it can. The water gets pushed out that way because that's the only direction which it can expand, and expands around the other side of Florida. And then because of the movement of the Earth, that swirling Coriolis effect, the water gets deflected and starts to move this way. That particular movement of water is called the Gulf Stream. And this is the hot water coming out of the Gulf of Mexico that gets pushed out into the Atlantic. It's in a straight line shot out into the North Atlantic gyre. This ocean current is the one we are going to talk about the most, because it's the one that really influences and drives the weather in the entire eastern United States and even further away from the United States. You can see it on a thermal imaging. There's our Gulf of Mexico. The water gets hot, pushes out across Florida, and then it becomes part of that North Atlantic gyre. And you can see the warm water gets all the way across the Atlantic Ocean, actually hits Europe. The Gulf Stream, even though the water is over here just to our south and it's close to us, it significantly impacts the weather in England, Norway, Iceland, and all of Europe. You can see it here. You can see how far-reaching the Gulf Stream is. It impacts all of Northern Europe because Northern Europe is north. They don't get as much direct sunlight as we do. Look at the latitude here. Latitude here versus the latitude in England. They're way far north compared to us, and yet their temperatures are not nearly as cold as you think they would be, and that's because of this really powerful Gulf Stream that brings nice warm water to them. Now, I want to point out these two locations here. We've got England and we've got Massachusetts. Massachusetts is a little bit further south of England. So we would expect Massachusetts to be a little bit warmer than England. Because even in ancient historical times, it was known that, hey, the further north or south you get, generally the colder you are because you're not getting as much sunlight. And in the early settlement period of our country, the settlers, the Puritans, the pioneers, they came from England and settled in Massachusetts. And their thought was, hey, we're going south. I know that where it is on the planet, Massachusetts is south of England. So therefore, it must be warmer, right? Well, if you look at this map, Massachusetts isn't hit by the Gulf Stream, whereas England is. So Massachusetts doesn't get the benefit, especially in the wintertime, of that nice warming effect of the Gulf Stream. Massachusetts is actually on a cold water current coming down from Greenland. So Massachusetts was a lot colder than they expected. I'm talking about the early settlers than England. As a matter of fact, that very first winter that the Puritans and the settlers came to Massachusetts, they almost died off because it was so much colder and the weather and climate was so much different than what they expected based on the latitude they were coming from in England. Now, the Gulf Stream also explains some very stark differences between the climates of Greenland and Iceland. Here is Iceland, and you see Iceland, it's not very icy. Iceland is actually very green, and you might have heard that before. There's lots of grass. It's almost lush, especially in the summertime. And here's Greenland. Greenland is very icy. There's very little green at all. And you might have heard the story about the false information given out by the Vikings. Now, Iceland actually has a real name that had to do with it being icy because there were some early Vikings that settled onto the north side of Iceland where they were exploring it in the wintertime. And yeah, it still gets cold, and some of the bays up there especially get iced in. And they got trapped for winter. And one of the Vikings wrote about this icy land where they were trapped for the wintertime, and hence the name stuck. Now, Greenland, on the other hand, one of the Vikings wanted to get people to go from Iceland to Greenland, trying to settle his own colony, and to entice people to go over there, he called it Greenland or Greenland. And people were like, "Oh, it's green, it's lush. I'm going to go over there. It sounds cool. I'll go there." And then they got there, and it was actually a lot icier. Well, these two locations are neighbors. What explains the difference? The answer is in the ocean currents that impact their climate. Greenland is surrounded by the Labrador Current. You'll notice on this map, those are drawn with blue lines. That's cold water from the polar area. So Greenland actually ends up being pretty cold. But if you notice where Iceland is, Iceland gets a lot of energy from the Gulf Stream. Even though it's not in the Gulf of Mexico, it gets that warm water from all the way down there by Florida, and it makes Iceland a lot warmer than you would expect it to be. Now, why is the Gulf Stream such a powerful current? This is some level of understanding that I really expect you to know. First of all, the Gulf of Mexico is pretty small and it's pretty shallow. And we know that a smaller body of water will heat up more than a bigger body of water. Think about it as like the Pacific Ocean versus the Gulf of Mexico. It's really hard for the Pacific Ocean to get hot because it's such a big bucket of water. And the Pacific Ocean's got a northern part and an equatorial part. So the cold and the hot water can always mix. Now, the Gulf of Mexico is only far south, and it's a small bucket of water. The depth here, Pacific Ocean is 13,000 feet deep, whereas the Gulf of Mexico is only 5,000 feet deep. Well, that means there's a lot more water in the Pacific Ocean, and it just can't get that hot. It's the first reason why the Gulf Stream is so powerful, because the amount of water is much, much smaller, and a smaller amount of water can get really hot. Now, the Gulf of Mexico is also pretty far south. It's getting a lot closer to the equator, so all of the Gulf of Mexico always gets hit by strong sunlight. If we think about the Pacific, well, we've got parts of the Pacific Ocean that don't get much sunlight, parts that are really far north and south away from the equator. But with the Gulf of Mexico, all the water in the Gulf of Mexico is always getting a lot of sunlight, so it's going to be hot. Matter of fact, this summer I was there fishing, went on my dad's boat, and decided I would take a temperature reading. The water in the Gulf of Mexico was 91 degrees. That's really hot water. We think about a 90-degree day, and we'd say, oh, that's a hot day. Well, that gives you an idea of how hot the water is in the Gulf of Mexico. Finally, the water's only got one place to go, so basically all of the hot water comes out and goes the same direction. That makes it a very strong jet or stream of water because it's all coming out this way together. If Mexico wasn't here and some of the water were able to go that direction, the Gulf Stream would not be as powerful a current. But now, the way our geography is set up, and you can see it's only got a very small way to come out, it's going to be all the water going one direction all at the same time, which makes for a very strong current, and that explains why it can shoot all the way across the Atlantic to England. Let's look at another example. Think about the Mediterranean. The Mediterranean is pretty far north. It's a lot further north than we are. So we wouldn't necessarily think of it as being too warm. However, if we look at a thermal image, the Mediterranean is a pretty warm bucket of water, especially for as far north as it is. And here's the reason. It's an almost closed system. That water can't mix with the cold water. So the water kind of stays trapped in there, so it stays warm. Remember, once it gets warm, it's water. It doesn't heat up and cool down that easily. So it just kind of stays as a nice warm bucket of water, even for how far north it is. Another example, let's talk about India. And we're talking about that Indian Ocean. We just said earlier, there is no northern part to the Indian Ocean because Asia here is in the middle. So this water here down near the equator gets hot and it wants to expand, but it can't because all of this land is in the way. It also can't be mixed with the cold water. We can't mix these two. So the hot water stays really hot, which means India stays really warm. And up here, it always stays really cold because there's no way for those areas to get any heat from the water down here at the equator. And you can see that in a thermal image. India always stays real hot because they can't have their hot water go away from them and take heat. Up here, northern Russia, they can't get any of that heat from that water coming from India, from the Indian Ocean, so they stay exceptionally cold. Now, the South Pole versus the North Pole, we referenced this already. The South Pole is all land. So here in the middle of the South Pole, you're a long way from the ocean. So even though there is hot water coming your way, it can't reach you because you're not on the coast. However, the North Pole is all water. So warm water from the equator can come up here and make the North Pole a lot warmer than the South Pole. And you'll notice the average temperature North Pole, -40 in the winter. Yeah, that's still cold, but it's not like the South Pole at -76. And the difference is the movement of the water that can bring you some heat. Now, I expect you to make note of these ocean currents because these are the ones that make a big deal to the United States. You need to know where they are impacting the country and is it a cold water current or a hot water current? So draw yourself a rough sketch of the United States. It doesn't have to be pretty. I just need you to draw these currents and know their names and are they a hot water or a cold water current? Now, those cold and hot water currents, California is on a cold water current. And this is what surfing is like in California. Even in the winter, even in the summertime, a lot of surfers will wear wetsuits. What's that tell you about the water? It's cold because it is a cold water current. However, surfing in Florida and on the East Coast is a warm water event because the Gulf Stream is a warm water current. Let's talk about another example here. And we're going to look at the Labrador Current, which comes down this way and hits this part of the country, affects all of the Northeast and Canada. I was up there this past summer, and I went to a beach right here in Halifax, Nova Scotia, which gets hit directly by that Labrador Current, which is a cold water current coming right by them. Went to the beach, it was beautiful, and I stuck my thermometer in there, and it was 59.5 degrees at the end of summer. That's really cold. That's unpleasantly cold. You don't want to go swimming in that water, although some people do, because it's chilly, it doesn't feel good. But then I went about 100 miles away, and I went over here to Prince Edward Island. And I got in the water there, and there the water was 74 degrees. Unfortunately, my picture, something happened to it. I was going to try to post that on here, but I don't know, disappeared. 74 degrees. How can it be so much different only 100 miles away. Well, the difference is Prince Edward Island is in the Gulf of St. Lawrence, and that water is coming from rivers and lakes like the Great Lakes, and it's not nearly as much water, and it's not way up by the poles. So the water here in the Gulf of St. Lawrence ends up being 74 degrees. So where do people in the Canadian Maritimes, this part of Canada, go if they want to go to the beach? Well, they go to Prince Edward Island, and they go to the beaches there because the water there is much more pleasant. So that's the end of the presentation. At this time, you can bring me your notes to get a done stamp and be ready for the notes check when we have it.